We will look closely at the range of a projectile, assuming that we can neglect air resistance. Although we will show the kicking of a football, our analysis will apply to any projectile for which air resistance can be neglected. We will not use numerical values for the initial speed and the launch angle. We will instead use the symbols v0 and theta. This might seem more difficult, but it will give a more general result. Range is the horizontal distance traveled by a projectile, assuming that the projectile returns to the same height from which it was launched. The component of the initial velocity in the x direction is v0 cosine theta, and there is no acceleration in the x direction. We will call this velocity component v0x, and since there is no acceleration in the x direction, v0x remains constant for the entire flight of the ball. The range r is the horizontal component of the initial velocity multiplied by the time for the trip. So if t is the time for the trip, r equals v0x times t. We want to get the range in terms of just v0 and theta. To do that, we need to express t in terms of v0 and theta. We will use the vertical motion to determine t. Y is the y component of the displacement of the ball, and y equals 0 at the beginning and at the end of the flight. We will use this fact to determine t. The component of the initial velocity in the y direction is v0 sine theta. We will call this velocity component v0y, and we are interested in the time, t, when the football returns to the ground, which is located at y equals 0. We are interested in the time t when the football returns to the ground. Since we know v0y and y, we can use equation 3.5b in the textbook to determine t. We might want to use the quadratic formula to solve for t, but for this equation there is an easier way. We can easily factor this equation. If we multiply two numbers and the result is 0, one or both must be 0. T equals 0 occurs at the start of the flight, so the other value of t must occur at the end of the flight. Therefore, the time for the flight is given by t equals minus 2v0 sine theta over ay. We now know how long the flight took, and we know that the constant horizontal component of the initial velocity was v0 cosine theta. The range is this velocity component multiplied by the time of the flight, so we can get an equation for r in terms of v0, theta, and ay. This is a nice result because if we know v0, theta, and ay, which is negative 9.80 meters per second squared, we can calculate the range. We now have an equation for the range for the case where air resistance can be neglected. The textbook says, when air resistance is absent, the maximum range results when theta equals 45 degrees. Let's see if we can prove that this is true. We will use the trigonometric identity 2 sine theta cosine theta equals sine 2 theta to rewrite the equation for r. The maximum value of sine x is 1, and it occurs when x equals 90 degrees. So for maximum range, we must have 2 theta equals 90 degrees, which means that for maximum range, theta equals 45 degrees. A question for the student. On the moon, the magnitude of the acceleration due to gravity is less than it is on the Earth. Would a football player on the moon be able to kick a football a longer distance, a shorter distance, or the same distance as on Earth?